And then I'll give you the test next Thursday. Okay? So, what we're going to do is we're now just going to apply perturbation to the major perturbing parts to the hydrogen atom. And those include the fine structure, and the fine structure is going to be a relativistic correction plus a spin orbit correction. And then we're going to add in, well, I guess the Lamb shift I talked about a little bit in hyperfine. So let's start off with relativistic correction. Okay, so perturbation to the hydrogen atom.
So we're doing section 6B.
Yep, that's here we're going to start. Okay, so here we go, 6.3. Okay, let's do the hydrogen atom. So hydrogen atom, we have a proton, and we have an electron. All right. When we write down Schrodinger's equation, we're going to write down the time-independent equation. It's going to look like this: H0 times psi n0 equals En0 psi n0. What are our solutions? Psi n0s go to, tell me.
Psi A, psi B.
Psi n, L, ml, right? So for every n, we actually have n squared degenerate solutions, right? All right, so it would be like this. And we have En0 equals minus 13.6 EV over n squared. So remember the restrictions on L. L is, for L, it's 0 all the way up to n minus 1, and then minus L is less than or equal to ml, which is less than or equal to plus L. And so we have an n squared degeneracy within n, right? So in other words, this psi n really represents n squared bases, right? So it's complicated. But to me, it's still great that we have this complete analytic solution to the hydrogen atom. I mean, that's great. Everybody okay? Okay, and let's just write it down, where H0 equals EK plus EP equals minus H bar squared over 2m del squared plus V of R. And V of R is minus 1 over 4 pi epsilon naught E squared over R. Okay. So the first thing is to realize we're going to do the relativistic correction. Okay, why are we interested in relativistic correction? Because Schrodinger's equation is, it's not relativistic.
You have to make it relativistic first.
Okay, so we have to make it relativistic. Okay, before we had EK equals 1/2 mv squared equals p squared over 2m. All right, is that relativistic?
No.
That is not relativistic. Okay, what do we know is relativistic? We know that the total energy equals gamma v mc squared. All right, and we know if V equals 0, that gamma equals 1, and that E total is essentially E rest energy equals mc squared. Everybody agree? I'm going fast now. Okay, so therefore, if I take E total, how about this? EK equals E total minus E rest. Is that a good statement? The total energy minus your rest energy, that's what your kinetic energy is?
Yes.
Okay, so when you do that, you get a nice relationship. That's one way to get it. Another way to get it is this. We also know that E total squared equals P squared C squared plus M0 squared C to the 4th. Right, so therefore, so here this would equal EK equals, let's see, gamma minus mc squared times gamma minus 1, right there. Or you could write it like this: EK equals, E total is the square root of this thing, So it's going to be the square root of p squared c squared plus m0 squared c to the fourth. And then minus e rest. So if p equals 0, if v equals 0, then p equals 0. By the way, this is the 3 vector p, this is not the 4 vector p. So then e total equals e rest, which equals the square root of m0 squared c to the fourth, which equals mc squared. So ek also equals this, mc squared. All right? So what happens is this looks like, this you can rewrite as mc squared. I'm taking this right out of Griffiths. You should go through and do all the steps for yourselves. I expect you to be able to do all these steps by yourself. But he rewrites this as, he factors out an mc squared. So it looks like the square root of 1 plus p squared c squared over m squared c to the fourth minus 1. Alright, or he writes as, and then this, so this becomes p squared over c squared. So this becomes p over mc quantity squared. Yeah, we okay? Take a binomial series expansion of this. No problem. Is that cool to do?
Yep.
Sure, we've got a c on the bottom. All right, so it's going to be small. When you do this, you get a brilliant result that ek equals, and I encourage you all to do this, so it's something you should be able to do on your board with a little bit of encouragement. You get 1/2, well, you get p squared over 2m plus, minus p to the fourth over 8m cubed c squared. M cubed c squared plus higher order terms. Why are you very happy when you look at this expansion? What's the leading term?
MC squared.
It's the kinetic energy that we used, all right?
Same energy we've been using.
And so if I wanted to represent a better Hamiltonian, right? A more true Hamiltonian, what would I want to do? I would want to say, therefore, a better Hamiltonian is E total, maybe, should equal H0 plus H prime relativistic, where H prime relativistic is equal to what?
Minus p squared over, the h of the...
Oh, now we're gonna...
So this is just the Hamiltonians. So in other words, this is giving us the form for the Hamiltonian, because this is the form of our original H0 Hamiltonian. What is this?
That's the picture.
That's the perturbing part. So what is our perturbing Hamiltonian for the relativistic correction going to look like? It's going to be that. So it's going to be minus p to the fourth over 8m cubed c squared. Okay, now, without looking at you books, everybody look at me. Right? What is En1 equal to? En, let's put in relativistic. So let's look at the first order relativistic correction to En1.
Could be psi n0.
It's going to be
psi
psi NL right?
0.
Okay.
And the Hamiltonian
And what's the Hamiltonian going to be?
p negative p to the fourth.
Okay, minus p to the fourth over 8m cubed c squared, and then psi to the NL, right? Everybody agree? So what do you need? Well, do I know what the operator for p is? Minus I, h bar,
b over d.
partial del. Okay, right? Okay, so you put that in there and you get a fourth order thing, okay? So that's how you do it straightforward way, and then what you do now is you go and you do it and you grind through it. But when you have wisdom behind you like Griffiths in his book does, he does a trick.
It's approximately 1/170, 137, something like that.
Well, no, let's look at the trick, okay? So the trick he does is very interesting, okay? What he does is he breaks this into this, which you wouldn't get. I mean, you and I would not be able to get this right away. He breaks this into -1/8 m³ c squared, and then he puts a p here, p squared here, psi m l ml, and then a p squared here, psi m l ml. All right, which is fine to do because essentially what you're doing is bringing p squared of this operator over into the bra. Okay, now when you bring things over into a bra, what you've got to do is make it Hermitian and complex conjugate. But, I mean, you got to take the adjoint complex conjugate. But what about operators of observables? They have to be Hermitian, so you can move it right over there into the bra. Right? And then what he does is he says, so this is just too clever. Right? And then what he says is, here's the trick. The trick is H0 psi n equals En psi n0. Right, which is p squared over 2m plus v times psi n0 equals En0 psi n0. Or, you ready? That p squared times psi equals 2m psi n0 equals En0 minus v times psi n0. All right. So hold on 1 second. Yep. This will be, yeah, but I'm trying to see the next step, so hold on 1 second, guys. Oh, okay. Crap, let's see.
He plugs that p squared psi equation back into the bracket, does the integral, he gets
Okay, yeah, so what he does is, I think he does this. He takes these and plugs them in here. All right, so let's see. Gets -1/8 m³ c squared. And then this thing is going to be 2m En0 minus v times psi n0. All right, and then over here it's going to be 2m En0 minus v times psi n0, which comes out to be 4m squared, so it's going to be -1/2m c squared. All right, and then it's going to be essentially the psi n0 times En0 minus v squared psi n0, which he recognizes as -1/2m c squared, the expectation value of En0 minus v squared. Okay? So, And now it gets a little bit complicated. So he follows through this, and you need a lot of other information. And I want you to go through all that
You
information.
take the expectation, thinks that, well, it's just the expectation of the V.
Right, so then this becomes, so you square this, so it's the expectation value of En squared minus EnV minus V squared. All right, and then this comes out to be just expectation values. And then the expectation values of V are just the expectation values of 1 over R. And then, so you can do those calculations for the expectation. And I want you to go through these. So it's go through these in your book, all right? I'm not going to ask you to do those intervals, just follow through these things in the
E
book.
squared over 4.epsilon, not the number, and then.
Yep, and so what you end up getting is the following. Okay, that's the trick there. Now he just goes and does all that stuff, and here's what he gets. He calls it ER1. So E relativistic 1 equals minus En squared over, let's En0 squared, over 2mc squared times 4n over L plus a half minus 3. Okay, now note that 13.6, I think this is how it goes, I think. Yep, so 13.6 over mc squared.
13.6 squared.
Hold on. Is on the order of alpha squared. All right, so we can write the relativistic as equal to alpha squared En over 2 times 4n over L plus a half minus 3. So this is E relativistic 1. Or so far, En total equals En plus alpha squared En over 2 times 4n times L plus a half minus 3.
Should that have been minus 13.6?
Alpha squared is not minus, so it's got to be positive, so it's got to be minus 13.6. Yes, that should be minus. Right there. All right, so there's a lot of steps here, but what does it tell us about this relativistic correction? What order is it? How big is it?
Very small.
That's not good enough to say very small. So here's an En,
That's squared is.
and here's an En, right? So what are the big things that dominate here? En and En. En's on the order 13 eV, 10 eV.
Right.
What's the other big thing? Alpha
Squared,
squared.
which is 10 to the 10.
Alpha,
1 over
10 to
1.
the
alpha equals 1 over 137, so let's say it's 1 over 10 squared. So what is alpha squared?
101.
1 over 1,000.
Well,
Right.
100.
So 1 over 100 squared. Alpha is 1 over 100. And so alpha squared is 10,000. Right? 10 to the 4. All right, so how big of a correction is this stuff? So this is on the order of 10 eV. This is 1/10,000th of an eV, so that means it's 0.001. So 0.001 eV.
And the first one's negative anyway, right? So
Okay.
it's a negative 10.
Well, let's look at it. I don't know if it's positive or negative.
Well, En calculated was negative
Okay.
10.6.
Yeah.
So
It'll be minus, yeah. All right, so let's look at how this splits up. Here's what I did. Let's look at an energy level diagram. And let's look, for example, here's E1, which equals minus 13.6 eV. So this is under H0. Okay. So E1 is for NLML, right? It's a 1, 0, 0. So what happens is this energy comes out here, now it's going to split into this energy. So it's going to be, it's going to be 4 times 1 over a half, which is an 8, right? Minus 3, so it's going to be 5. So it's going to be about minus 5 times 0.001 eV. All right, so that's going to bring it down like this.
How's that minus?
Right?
If you get a plus 5, and then you have En, which is minus 13.6, wouldn't that make it a positive? Because En is negative, and you get a positive on that. And then you take a negative number and multiply it by negative, you get a positive.
That's a good point. I don't know which way that goes. I don't know whether they need it absolute or minus. I don't know which way it goes. Yeah, good question. Maybe try to figure that out. So Dale's right. En is minus 13.6. I was using it as an absolute value. So I don't know which way it goes, whether it goes up or down. I think it goes down. Because on the next page, it goes down.
What do you want first?
It shows it drawing.
So let's do it like this. I think alpha squared is kind of like the absolute value of 13.6. I think it's meant as a positive number.
Well, look at the original.
I know.
There's a minus sign there, and then is that number
Well,
on
it's
the
not,
right?
but check it out. It's minus En squared, so
Yeah, but
they
there's a
want
minus.
this value to be, this has to be minus.
Minus. And then is that positive?
Well,
So
look,
4 times
what they
1
want is this whole term for this correction is minus.
Yeah.
So I carried it down here, so the correction I should make is to write that as an absolute value, so it's a minus.
That would do it.
All right?
It's a different, it's not energy, so it's subtraction.
All right, and then what happens at E2? What happens here? And by the way, this is when we put on H relativistic. Not when we put it on, when we take it into account. What happens here? Now we have a 2, 1, 0, and we have a 2, well, we have 2, 1, and then minus 1, 0, 1, and then we have 2, 2, 0, 0. So these are going to split into 2, right?
Yeah.
So maybe one goes like this, and the other
They
goes
both go down a little bit.
They both go down a little bit.
3 halves by 3 halves and 1.
Okay. And so now, do you think we can measure the energies between, do you think we can measure 0.5 thousandths of an EV? And it's trivial with lasers. 5 thousandths of an EV is not a big deal at all.
No problem.
No problem. So can we test to see if this is true or working? Yeah. Okay, so that's the first step. Now let's do the second step, which is spin orbital. And by the way, the homework, the only homework I'm going to add in this whole section is 619. All right, and it's a fun one. All right, and then the rest of this section, I simply want you to be able to follow the arguments for how to do these things. So on a test, I might ask you to set it up, but I wouldn't ask you to do the whole thing. All right? So the next thing we're going to do is we're going to say, okay, this is great. Let's go back to H0. So far we have H total equals H0 plus H relativistic correction. All right, do you think we have more? And the answer is yes. All right, now the first thing that we're going to talk about in this more is look, is the electron is spinning, right? So it's got spin. The electron is a spin and a half. And because it's a spin a half charged particle, so it's a charged particle spinning, what does it make? It makes a little tiny magnetic dipole moment. In other words, a spinning charged particle looks like a little tiny magnet. That little tiny magnet is described by mu. So let's call this mu electron S. All right? Now, recall I did this derivation in class. Recall, mu for any angular momentum L is equal to G times Q over 2m times the L vector. Okay? So what is mu electron spin equal? It equals G spin, right? Then it equals, it's going to be minus because it's an E, right? The charge is going to be minus E. And then it's over 2 times the mass of the electron, and then times what vector? What's the angular momentum vector that's making this magnetic dipole? That's the spin. Yeah? Okay. Now, at the same time, I'm not even including the proton here, but at the same time, this electron is in an orbit. Okay, so this is the electron orbit. Now, the electron, is it a charged particle?
Yes.
Is it going around in a circle? Is it going to make a magnetic field? Is it going to be a magnet because of its orbit too? So what else do I have to include here? So maybe make this into a little tiny magnet. So now I need another magnet here. And what am I going to call this little magnet? It's going to be mu, magnetic dipole. It's going to be described by what angular momentum?
L.
It's going to be described by angular momentum L of the electron. So what's it going to equal?
G minus E.
Okay, so it's going to be minus G, but careful, what G?
The one of L.
Okay, it's going to be G for the electron orbit, and it might be different from G from the electron spin. Indeed it is. Okay, and then it's going to be times E over 2 times mass of the electron, and then what's the vector that makes the magnetic dipole?
L.
L. All right? All right, so that's one way to look at it. All right? So another way to look at it, so this is one way. Or, how about this? And this is cheating. Okay? Sit in the frame of the electron. All right? And if I sit in the frame of the electron, then I have a mu s. But if I'm the electron, right, and then, I'm kind of like, if I'm in the frame of the electron, right, then the whole atom orbit is kind of going around me because I'm not seeing that orbit, right? Everything's going around me. So what I'm seeing now is I'm not seeing the magnetic dipole of the orbit. What I'm doing is I'm feeling the magnetic field of the orbit. So if you sit in the frame of the electron feels the B field of the orbit, of the electron orbit. All right, now this is cheating, and the reason that it's cheating is because you can't really, because if you sit in the frame of an electron, is it an inertial frame?
Yes.
Electrons move.
If you're in the frame of the electron.
Is that inertial?
No,
Why not?
because it's moving.
Well, look, all
You're
inertial
moving
frames
it.
are inertial to us, some other frame.
It's accelerating.
It's
going
accelerating.
around.
Yeah.
It's
That's-
moving around.
Okay, by definition, an inertial frame is a non-accelerating frame, but it can be moving with respect to another one. But the electron, because it's in an orbit, even if it's constant velocity, by definition, because it's in an orbit, it's accelerating because it's changing its direction. Okay, so this isn't a 100% legitimate argument, and the answer to this, to do it correctly, is on page 273, and it's called the Thomas precession, and it's a correction, and there's a couple nice footnotes to how it's done. Okay? But in any case, we'll add in the Thomas precession correction later on. In any case, let's imagine that the mu s is in a B due to